All righty, it's just about noon. Let's go ahead and hold forth. I sent you a homework assignment, which I was going to go over first thing, but I think we'll go ahead and try to get through some of the lecture stuff and then go back. I will, either this time or next time, I will review that. It will probably be due a week from Thursday, is what I'm thinking. I haven't done, I'll send you out an official due date, but I mean, there's quite a bit of work in that thing, and you know, it's fairly straightforward in most cases once you're familiar with the concepts, but we just haven't gotten through everything that's covered there. So I think I'll lecture first and discuss homework later. So this is where we wound up last time, and then I went off to the measure tool and demoed that, because the slides here are actually for a different program, the STEAM System Assessment Tool, which is the precursor to what's in measure. So what's here applies, but it looks a little bit different, okay, when you do it in measure. And we'll spend some time, but you need to get that measure tool, because you know, this week you need to start doing this homework, and measure will do a good bit of it for you. So what these programs do is they model the entire STEAM system. They do mass and energy balances, and they're pretty easy and straightforward to use once you know, kind of become familiar with some of the terminology and what they're asking for. And they really make evaluating projects very, very simple. You mean how to operate it?
Yeah, pretty much.
Yeah, I think so.
Okay, good.
I think if you will Google, you know, measure instructions, that sort of thing, I think they have some software, but it's I mean, it's pretty simple. Okay, so let's move on. This shows some a before and after simulation. So what this software does is it allows you to simulate a potential project. It will have different projects kind of built into it, and you simply have to turn on a project in order to get it to simulate it. So you build the base case model, and then you tell it, for example, here, we want to investigate a blowdown thermal energy recovery system. Now, we ran the numbers on this last time, and I think we had come up with numbers like $215,000 a year was our estimate on recovering this flash steam and the heat exchanger. So we will then do it in the software, and lo and behold, the software says you're going to save $265,000. So it turns out it's even better than we had thought with our simple hand calculation. I don't know if you can read those numbers up there or not. They're fairly small, but you can see it's showing a fuel cost savings of $262,000 a year and water savings of $3,000 a year, for a total of $265,000. We did not even try to do water cost savings on our hand calculations, which, I mean, we could have, but we just didn't. Okay, so the question is why do we get more savings out of the software than we did in the hand calculations? And there's a couple of reasons. We can see down here, the energy recovered to the makeup water is not subjected to the boiler inefficiency. And so when we did our hand calculation, now we could have taken that and divided by the boiler efficiency or an estimate of the boiler efficiency, which would have made the savings larger. So that is something that you could do, but we did not take the boiler inefficiency into account. And steam generation makeup water requirements are reduced because of the recovery of the flash steam, and that's that additional $3,000 that showed up. So, you know, we're trying to make a case here for using the simulation software instead of doing the calculations on, you know, a piece of paper or something that is a little less sophisticated. Project implementation costs should be less than $100,000. Additional benefits from blowdown energy recovery include boiler water chemical constraints can be reduced without incurring significant loss. You know, so that's less water that we have to make up water because of the recovered flash steam. That's pure water that stays in the system, so we have to do less chemical treatment. Makeup water requirement is reduced. Many systems require cool sewer flows. So if you're not recovering heat from this blowdown, it's very common to take just regular water, you know, that you're purchasing and blend it with that hot blowdown before you can put it down the sewer, because the water utility companies don't want, you know, 200-degree water going into the sewer. It over time, it will damage their pipes, cause leaks, and cause them problems. So not only were you throwing away all of that in the first place, that before you could throw it away, you had to throw some more water in there to cool it down, and then you had to throw all of that away too. So that's another reason for recovering heat from the blowdown flows. Okay, another issue that we have to be concerned with, and this is what the overall model looks like in SSAT. That's a 3-header model. You see, you got a high pressure, medium pressure, and low pressure, and you have various turbines. The turbine pictures always show up, but you have to see if there's any numbers, if they're actually active in the model by looking right here. So this turbine is producing what, 698 kW, this one 1376, and this one 1161. So all 3 of these turbines are operating. And so what we're going to find, if I put in a flash tank and I take some of that blowdown, and the flash steam from the blowdown goes into the low pressure header, that amount of steam is not going to pass through one of those turbines. And so that's going to reduce the amount of power generation that I get out of that turbine that is affected. And so if you're doing hand calculations on the back of an envelope, you're probably not going to be able to include that, or it's going to make your life very difficult if you try to work through all of the thermodynamic states and and estimate this correctly to evaluate the project. So we can do that here. So this is what the SSAT evaluation looks like. We see up there under power cost, we've got a negative $70,000 a year. Well, that's because and when you look down under this, on the lower down here at the power import, we're going to have to import another 115 kW of electricity. And so that's going to cost over the course of a year $70,000. And that's because as I recover that flash steam and put it in the low pressure header, that amount of steam doesn't go through a turbine. And that means I lose 115 kW worth of generation. And that cost me $70,000 a year. Okay. The fuel cost benefit in this case then is $307,000. The water benefit is $4,000. And so I net out at $241,000. So you see, again, to get all of the effects on the system simulated in the analysis, we need a model of the entire steam system. Okay, so here's a summary on our blowdown loss discussion. Measured blowdown flow, we want to do that, and that's based on chemical analysis of the blowdown water and the boiler feed water going back into the boiler. We want to control blowdown flow. We would like to do it automatically, and that would be on the surface blow. The bottom blow, we just open the valve and throw that away for cleaning chunks of material out. But the surface blow really controls the boiler water quality, and we want to base that on probably electrical conductivity and then also water chemistry, where we send it off to a lab and get good results back. So that's control water chemistry. One thing you can do is improve your feed water quality. Well, how can you do that? You can clean up your makeup water, or you can return more condensate. The condensate is considered pure in most cases, and so if you can bring back some that you're dumping on the ground or throwing away, that's less makeup water, that's less minerals and stuff that you're putting into the system, so you have less to clean up. And then, of course, recover flash steam to low pressure systems and preheat inlet streams. The photograph is an actual blowdown, a plate and frame heat exchanger was used in a chicken rendering plant of all places. And that was their boiler, but they had put in that blowdown heat exchanger. That's what it looked like. It wasn't working very well when I was there. It needed to be cleaned, which is not unusual. So not only do you have to put the systems in, you have to maintain them. That's kind of a pain in the rear, I guess. And the other, the fire tube boiler picture is just a little bit of a cartoon, just illustrating a full system. We see the low pressure steam, that's the flash tank. So the blowdown comes out of the boiler, goes in the flash tank, the flash goes out to some useful purpose, and then the liquid falls down into that heat exchanger where we're putting some kind of a water stream in, cool and bringing it out warm. We also show a sample cooler. So when they take these samples, they just have a little bleed line, and that usually goes through a little box that has some cool water running fluid through it just to cool it off so it doesn't burn the technician, the guy that's actually working with it, because it's pretty hot when it comes out there. And then so you do your analysis on it and then toss that little bit away. Okay, questions or comments on our blowdown discussion? So now you should have a pretty good idea what blowdown's all about on a steam system and a boiler. So let's look at stack losses. This is a big deal. Stack losses are typically categorized on the basis of temperature losses or combustion. Okay? Combustion analysis is a method generally used to determine stack losses. Unburned fuel in the exhaust gases and ash are components of stack loss. So in the, on a coal-fired boiler, any carbon that's left in the ash is considered a lack of carbon burnout, because that's carbon that you purchased that you did not combust to CO2. And the term for that is loss of ignition, LOI. So in the coal industry, coal boiler industry, LOI means loss on ignition, and it refers directly to the amount of carbon that you measure in your ash. So you ask somebody what's their LOI at a coal plant, they might say, it was 5% last time we had it measured. So you're not going to know that. What you have to do is you have to take a sample of the ash and put it in a nice little container and send it to the laboratory, and they do a chemical analysis on it by different techniques, and they can tell you what percent of the solids in that sample are carbon. And so you don't want to see much carbon left over in your ash. Okay, so let's look at the temperature component. flue gas temperature loss. Flue gas exhaust temperature must be considered along with ambient temperature. Okay, so we have some tables, or Oak Ridge has a calculator. Or, you know, it turns out this stuff is pretty easy to evaluate. You usually just go look it up someplace. But so the definitive temperature is the net, NET, net stack temperature is the definitive measure. And that is the difference between the flue gas exhaust temperature and the input air temperature. So you subtract. So you have to do that subtraction. And then you take that net temperature and you go to your tables to look it up. And then, of course, your boiler temperature is typically at the exit of your last heat exchanger. So we'll see there's devices called economizers. And they're heat exchangers that go in the stack to preheat the feed water before they go into the boiler. Now, if your boiler does not have any sort of heat exchanger after the boiler itself, after it comes, you know, directly out of the boiler, then that's the temperature that you want. If you have an economizer, you want the temperature of the flue gas coming out of the economizer, because you have retained that heat in your steam system. Okay, so you don't want to inordinately penalize your steam system, because you may have 550, 575 coming out of the boiler, but you may have 325 coming out of the economizer. So you want to take the temperature right at the exit of the last heat exchange surface to properly evaluate your boiler efficiency. Now, some people will have a temperature sensor way at the top of the stack, because environmental EPA wants to know the temperature of the gases that you're actually putting into the atmosphere. Well, that's well and good to know that temperature, but that's not the temperature that we want to evaluate the stack loss, because that flue gas was probably 100 degrees hotter when it left the last heat exchanger, and it cooled down in the stack as it was flowing through all the ductwork before it gets let loose to the atmosphere. Well, that heat that's lost in between didn't do us any good, you know? So when we evaluate the boiler efficiency, we want to know the temperature at which the boiler quits recovering heat from the flue gases. Okay. A lot of energy resides in flue gas. Certainly the temperature indicates the energy content. Most common factors influencing flue gas temperature are presented as follows. So these are some of the factors that we have to consider. Well, first of all, what boiler did you buy? Did you buy the cheapo boiler that has not much heat transfer surface in it? The one-pass boiler on the left just has that big tube, which is the combustion zone that the burner fires in. It goes down one time, the gases turn and go up the stack. Well, they don't have much of a chance to transfer a lot of heat. So that thing is probably, it's cheap on the front end because you don't have to buy much metal, you know, but it's not going to have a near as good efficiency if you buy the three-pass boiler, where, you know, we have the combustion zone, that's one pass. It goes up a little bit and it goes back to the left, that's the second pass. It goes up to the top section of the boiler and it comes back to the end, that's three passes. Well, it's got way more opportunity to transfer heat into the water and create steam. So you would expect the three-pass boiler, if all other things are consistent, to have a much lower stack temperature than the one-pass boiler, because it's got a whole lot more heat transfer surface in it. So boiler design, and there's other things that we'll talk about, but boiler design is one thing that's critical that you have to consider. You know, if you've got two boilers, one's a four-pass and one's a two-pass, well, you've got to expect the four-pass is probably going to be better as far as efficiency is concerned, and it should have a lower stack temperature. Okay, here is the feed water economizer, one of the slides. And so that red serpentine coil coming in the bottom down here is flue gas, not flue gas, feed water is inside the tubes. And it goes through this, and this is just a coil with the hot flue gases going over them. And then it comes around and is introduced into the steam drum. So that's the feed water coming back in to maintain the water level inside the boiler. And of course, then the flue gases are getting cooled down. We typically expect to see about a 40-degree Fahrenheit increase in feed water temperatures going across that thing, usually someplace between 35 and 45 degrees. When you go into a plant, you can try to look at a logbook and see if that delta T is consistent over time. It's possible for those heat exchangers to get dirty, fouled. If they have to be cleaned probably every year, year and a half, 2 years. You need to take that thing apart and clean it out good. If you see that you're running a 20-degree delta T on feed water, and you can look back a couple years into the books, into the records, and say, wow, we used to run 35, 40, now we're running 20. Something's changed. If the flows and temperatures are comparable, then you probably have a dirty heat exchanger. You can look at the flue gas temperature. If the flue gas temperature is creeping up over time for the same inlet and steam production, you got to say, hey, it looks like we got a maintenance issue here, and somebody needs to address that. Obviously, if you have that economizer, your exhaust gas temperature is going to be much lower than if you don't have it. Okay, flue gas temperature limitations. Well, how can we screw this up? You get a good idea. There's always a way to screw it up, right? Murphy is always working. Well, if we cool this flue gas down too much, we can have bad actors start to condense. And when they condense into the liquid state, they can eat holes in things. They can condense to concentrated acids, and they just eat holes in ductwork or whatever material, whatever metallic, typically metallic surfaces they can come in contact with that are not designed to handle that type of acid, okay? And so there's two things. You see sulfur listed on here. So if you have a fuel that has sulfur content, as you cool flue gases, it'll burn to what? Sulfur dioxide, but it will condense as sulfuric acid. It will condense to H2SO4. And y'all know from your chemistry lab, sulfuric acid loves to eat a hole in things, and it'll be quite concentrated, okay? So that's, as you start to cool down, that's our first point to which we have to worry about stopping in terms of cooling the gases. Now, if you're burning natural gas, okay, you don't have to worry about sulfur because there shouldn't be any sulfur in natural gas. If you're burning a fuel oil, if you're burning like number 6, high sulfur fuel oil, then you got a lot of sulfur in it. If you're burning coal, you've got sulfur. It depends on your fuel source. What are you putting in as to what you're going to get out in the flue gases. So we see the acid dew point, and you see a minimum recommended feed water temperature entering the economizer. That's the red line, and you see the acid dew point. So, if, according to this, what it looks about, 220, something like that, we can put, if we don't have much sulfur in the fuel, we can put as cold a water as 220 into that economizer. And the reason what's going to happen then, of course, the colder water you put in, right there where it first comes in, that's where it's going to condense. because that's the coldest water hitting that temperature of flue gas. And then as the water goes on through the heat exchanger, it warms up. And so then the flue gases in that portion are probably not going to get quite as cold. But locally is where you're concerned about the local cooling at any one point, because that's where that acid will start to condense and collect. So sulfuric acid is number one. If you don't have any sulfur, the next component is just water. If you get it cool enough, if you get it down, so you can get down into the 170s, 175, something like that, and you should be okay. But if you condense out water into liquid water, you've got CO2, you've got CO, you've got NOx. You can create a variety of acids in there. Carbonic acid is the combination of water with CO2 will form, what is that, no, I can't remember. I think I have it in here. I forget the formula for carbonic acid off the top of my head. But it's the combination of CO2 with that water. And again, it will eat holes in things. Back when Tech was on coal over here, they had an economizer when that system was built. And after 2 or 3 years of operation, they took it completely out of service. They cut it out because it was too large. It made the flue gases too cold. And there was a big duct that went across to the bag house that would separate the ash. And over the course of a couple of years, that acid, the water condensed, or it could have been sulfur in that case. Anyway, it condensed and it ate big old holes in that thing. And it cost them a couple $100,000 to fix. And they just said, no more. So up until about 3 years ago, when we went completely to natural gas, I would go over there sometimes and I would see 500, 525, 530 degree flue gas temperatures going out of the boiler, heading over to the bag house. And I kept saying, man, we got to put an economizer on this thing. And the guys that ran the place said, been there, done that, and we cut it out. I said, well, it was a control issue, It wasn't controlled properly. It got too cold, and they said, well, we don't care. So they were probably throwing away 5 to 7% on boiler efficiency. But they had a bad experience, and so their approach to fixing it was, hey, that causes me problem. I'm going to get rid of it, and I'm not going to have that problem anymore. Well, that's true. They also didn't have a very efficient boiler steam system in those days. Now, what we have today is quite good. But anyway, so you do run into this. Okay, condensing economizers. Okay, so a standard feed water economizer like this guy is probably going to exhaust gases at maybe 250, someplace 240 to 300. It's going to be your exhaust temperature. So you're still going to be throwing away a fair amount of thermal energy. So you can put a second economizer on this that's called a condensing economizer. So a condensing economizer is meant to cool those flue gases all the way down to 100 degrees, 90 degrees, whatever it's designed for. Well, so you're going to get acids like crazy. Yes. These things are going to be ceramic. They're going to be Teflon coated. They're going to be materials that are designed to hold up under the acid attack. And they're expensive. And I've seen some of them. You don't see them all the time. But I mean, they are out there. In the right situation, they are tremendous. So, but it depends on your operation, as we'll talk more about. So let's go through the slide here. Condensing economizers can improve boiler efficiency more than 10% in comparison to conventional boilers. Okay. Has anybody ever gone out and investigated a natural gas furnace system for a house? You ever looked into the literature? Well, they advertise these natural gas heating furnaces 95, 96, 97% efficiency. 96, 95, 96, 97. How do they do that? This boiler, when we talked about boiler efficiencies for natural gas, we said a good one was like 82 and a half. You might get one up to 85 if you're really doing good. Well, why can this big boiler be limited to 85% efficiency, and I can buy this little piece of equipment that goes in a closet in my house that's 95% efficient? And the answer is this 10%, those things are set up to suck the heat out of those flue gases all the way down to almost ambient temperatures. And that boiler, unless you buy this special condensing economizer, is going to put up those flue gases at 250, 300, something like that. And that's 10%. That's 10% of the fuel, of the energy in the fuel that you're throwing away because you can't cool those gases without them condensing acids. Well, that's a bunch of money. And see, these little systems are made, something little like that, they just make these little bitty heat exchangers in there, and I guess they coat them. I'm not sure what they coat. They probably just Teflon coated or something. But they go ahead and they pull the heat out of that thing down to maybe 100, 110 degrees, something like that, and it condenses. So that's why. Okay, so final flue gas temperatures can be as low as 75. Indirect heating units can heat streams to 200. Direct, we'll show the difference here in a minute. Direct condensing economizers can heat streams, fluids, to 140. Significant amount of relatively low temperature energy is recovered. Equipment is limited to fairly clean fuels. Okay, so think about it. In general, I got this big flow of combustion gases at, say, 250 degrees. And I want to cool it down to, say, 100. So what else do I have to have? I have to have something cold that I want to heat up, right? I can't cool these gases to 100 if I don't have another fluid, a gas or liquid, that's, I don't know, 75, 80, 90 degrees, right? Because how are you going to get that leaving gas temperature out of this condensing economizer to be as cold as 100 if you don't have something colder than that to put into it? Well, that's the rub. Lots of plants, lots of businesses, lots of different manufacturing concerns don't have anything cold enough that they want to heat up. Now, the perfect example of being able to do this, I visited Campbell Soup Company over in North Carolina. I did a big boiler study for them a number of years ago. Well, they are sucking flue gas temperatures down to under 100 because they're cooking soup all day long. They're making soup, man, they're making tomato, they're making chicken rice, they're making veggie, they're just making big old plant, big old boilers, they're making soup. They're making it like crazy. Well, what's the biggest component in soup? Cold water. So they're bringing in all of this cold water, and then eventually they put all the other stuff in there and they have to cook it. So they have to bring it up to, I don't know, 200, 300 degrees and hold it there for a while, whatever their recipe is. So they've got this constant stream of cold water. They've got these boilers operating with this constant stream of flue gas that would be 250, 300 degrees. They put those in a heat exchanger, and man, so they're heating up that water that's going in to make soup, 110, 100, maybe 130, 140, I mean, maybe 200, depending on the system and the design. And so that saves them, look at all the natural gas they save on cooking the soup because the water comes in preheated. So say that's what a condensing economizer can do. This chicken processing plants. You know, I can tell you about the life of a chicken. I've seen the hatcheries. I've seen the big coops where they grow them. I've seen the processing plants where they do them in. And I've seen the chicken rendering plants where they send the beaks and the feathers and everything else. You know what all that stuff gets made into? Chicken beaks and claws and feathers. You know what they make? They make chicken, they make chicken feed. They do. They make high protein. They make high protein meal that goes into animal feeds. It's amazing. They have these big rotating kilns that have steam supplied to them. Big old things, like, I don't know, as long as, half as long, well, I don't know, as long as these two classrooms for sure, probably, I don't know, 20-foot diameter, and they're tilted a little bit, and they rotate them, and they chunk it full of feathers and stuff, and then they cook it, and that stuff just rotates and grinds and cooks and grinds. It comes out this little reddish, kind of moist, granular stuff, which is high protein meal. And then they take that and they put it in animal feeds. So they feed the chickens back to the chickens. And it's a very aromatic experience. So they tell you your first day when you visit the plant, they say, you do what you want to, but we suggest you don't eat any breakfast. And you get there and you got to start walking around, and all of a sudden you walk in this room or something and you get this wafting of something, and you kind of, I never got anything above right here, but I had it here about 3 or 4 times, especially that first day. I'm telling you what, there are some aromas that you cannot believe. So anyway, the processing plant, they're always washing. You know, they're doing in chickens and they're processing all this stuff. So they're washing this, they're washing that. So they use all kinds of hot water. And so that's a good application for a condensing economizer. But, you know, if you're a plant, I don't know, if you're just making, I don't know, maybe you're making cement or something, or making some metal product. Maybe you're just machining metal. I mean, you don't have any big amount of water or any fluid or anything that needs to be heated up. So, you know, this is off the table for you, unless you can come up with some kind of an idea. Well, maybe we could, you know, raise shrimp or something. You know, we'll put tanks of shrimp and then we'll heat the tanks with the, you know, whatever. You know, you have to invent a reason to be able to use the boiler heat, which can be difficult. Okay. I always feel good when I get my chicken story in. Okay, so there's an example of a condensing boiler application. So let's see what we got here. So the pink box sitting on top of the Flue, that's the standard economizer right over here with the red pipes. Come on, give me my pointer. Here. Let's see, I can't see which way we're going in, but so we're putting, what's it, main steam header. So yeah, we got steam coming out of the boiler here. Here's our pumps, deaerator, we're pumping back. And so we go through this heat exchanger and we preheat. So this is a standard economizer. And then we pull off over here and we come down, and we do have another fan system. And then we've got our makeup water. We got cold water coming in here that's then is pumped across this coil. So then we preheat it a second time, and then this is going back into the steam system. Now, this would be for a situation where maybe we're not returning hardly any condensate. You know, like if you're cooking tires, Bridgestone, they don't return. They don't, because they got these tires and that steam comes in contact with the rubber. And so if they try to bring that back, condense it, bring it back, they bring back all these little bits and pieces of rubber. And those boilers don't really like having those little bits and pieces of rubber in there. So it causes all kinds of fouling and issues. So they may do some heat recovery, but they don't want that condensate. They don't want that water back. So that means they're going to dump it, which means they may have some other like space heating that they bring back, but all of the steam that cooks tires, they don't want that condensate back. It's way too much trouble. So they dump it, and then they got makeup water coming in. So they got a lot of makeup water coming in. So perhaps that's enough water to make the economics on this work. These things are quite expensive. I know Archer Daniel Midland has invested in some at some of their food plants. And the guys I've talked, they're like $650,000 to $1 million to put all that stuff in. So it's got to be a big boiler, and it's got to be, you know, big loads and all that stuff to make the economics work. Okay, so this is the indirect contact condensing economizer. And so, you know, we're coming over, say we show flue gas 325 from boiler after heat exchange in feed water economizer. So we've already gone across the conventional economizer, and we probably had 475, 500 degrees coming right out of the boiler. We put that across the standard conventional economizer, got it down to 325, and now we're going to put it across this indirect contact condensing economizer. And so that's what these coils are in here. So we're showing 45 to 85 degree water being pumped in through this coil. We got some temperature control here. And we're showing 200 degree water going out. So if this is Campbell's Soup Company, instead of starting to cook soup with 45 to 85 degree water, you're starting from 200. And so the hot water heaters over there that boost that on up to whatever they need are going to use far less energy. So that's the idea. And then, so we're showing a stack temperature of 100 to 120 degrees, which is well down in the condensing range. And so you would have water, if you had any sulfur products, you would have sulfur dioxide falling down into this. And so all of these materials have to be fairly exotic to be able to stand up to the corrosive environment. So that's the indirect contact economizer. Here's a direct contact. So here, what we have is, here's our flue gas inlet temperature, and it's just going to flow upward through a packed bed. Could be ceramic or stainless steel, ball bearings, something like that. And that's a heat transfer mechanism. So we've got a heat source coming up through here. We've got a little circulation loop over here. And so I got a little pump that's going to pump through a heat exchanger. So I've got fairly warm water down on the bottom of this thing, and I'm going to pump it through the heat exchanger. And so I'm showing maybe 90 degree water coming in. It could be boiler makeup going out at 135. So this is the useful energy that I'm recovering. And so at 140 in, 95 out, and it just constantly gets sprayed, falls down over this. So some things we get a scrubbing action. So we're going to scrub some things, some emissions, because that spray water and that flue gas are in direct contact. So that's a good thing. Notice I show blowdown down here because I'm going to have a buildup of things in this water. And so I'm going to have to control the water chemistry in here. So I'll have to check that, blow it down, add water to this to keep the proper level in it. And I'm not showing nearly the temperature I had, you know, I'm showing 200 degrees here, whereas I'm showing 135 over here. So this is not going to produce as high a temperature for me. But the reduction in emissions from the flue gas might be an important part of this, for sure. Because the EPA, man, their emissions are everything these days, trying to keep the environmental people happy. So that's the direct condensing economizer. Okay, other things that affect boiler flue gas temperature would be boiler load. Just in general, as I increase the load on the boiler, I expect to see the flue gas temperature increase. Okay? At 100%, like on this chart, at 100% load, so if I had a 2,000 horsepower boiler like Tech does, my steam production rate would be what? 34.5 times 2,000, which is what? 69,000 pounds an hour at full load. And when I was there, this thing says I should expect a 525 degree stack temperature. Now, that would be before an economizer. If I'm running at 50% load, I would expect about a 425 degree Fahrenheit stack temperature. So if you're going to compare stack temperatures, you got to do it, you know, to have a fair direct comparison. I need to have the same boiler load, the same inlet air temperature, and of course, assuming that the steam temperature is the same in order to properly compare. Because sometimes you want to say, well, I don't know if that boiler seems like that stack temperature is creeping up. Maybe we need to open this thing and clean it. Oh, that's right. I need to show you guys the borescope video. I did find it. We'll do that here in just a second once we get finished stack temperature. Okay, another thing that can happen is sometimes there's baffles and there's a proper flow path for combustion gases, flue gases through the boiler. It's possible to have a failed component. For example, this is the proper flow path. This is the combustion zone, and we flow up, and then we have baffles. We flow down across here, back up across here, and back out across there. Well, what if this guy's broken, and a lot of these flue gases are just bypassing and not following the correct path through the boiler? Then obviously they're not going to have an opportunity to transfer the correct amount of heat. So, you know, making sure that the flow path is correct and that we don't have some sort of a failed component is critical. What about fouling? So, you know, we've talked about waterside fouling is scale, and oh, this is too perfect. You guys need a break here. I think I can now find my borescope video. I certainly hope so. I ran it to ground the other day. Let's see. Document 4260. Did I put it in Steam? I bet I put it in Steam. Let's see. Oh no. Oh no. Oh, not again. There it is. And it's going to play. All right, so this is probably a 2-inch diameter tube. And this thing goes on for a little while. They're getting everything set up for a little bit. July 11th of 07. There you go. Now, you see all that white stuff? That's scale. You see very little bare metal on the inside of this tube. So the story the company tells is that they fired a guy 3 or 4 years before I got there, and he managed the boiler house, and he didn't do a very good job on water treatment. And he was there, he probably ran things for 5 to 7 years. And this is what happens when you ignore your water chemistry for 5 to 7 years. Look at all that crap. Now, occasionally, you'll see a place where it's cracked off and you can see some bare metal. But You see, there you go. See, occasionally. The rest of that stuff, that whole area is coated. That's insulation. Makes it hard. Makes it hard to transfer heat. You're burning all that fuel. Those hot gases are on the outside of that pipe. That pipe's full of water, and you're wanting to generate steam inside that pipe. It's probably some of them are no more than 3-inch diameter. It's something like that.
So they like to do something to dissolve that scale, or they have to resolve?
What's that?
Do they have to do something to dissolve that scale?
Yeah, they have to acid clean it. Hydrofluoric acid. Bad stuff. So they have to put a fairly concentrated hydrofluoric acid solution in there and pump it around for, I don't know, 4 to 6 hours. And then they have to clean up all that stuff. And then they're likely to have leaks for a while because all that acid will eat gaskets and fittings and eat stuff that they don't really want it to eat. So, I mean, what a pain in the rear. But I mean, this was, I don't know, 5 or 6% on boiler efficiency. I mean, you get to a point you have to. I think it was $35,000, $40,000 to clean, and they had 2 of them. They had the north boiler and the south boiler. They're very creative in boiler names. This is north, this is south, we'll just call them that. At some point, they pull this thing out and you can actually see a little bit of the boiler room around it. You can. So what they do, they open up the steam drum and then they feed this down the tube and they feed it all around until it pops out the other end, and then they pull it back out and they do another one. And there's a lot of different tubes to look at. I guess they look at all of them. I don't really know. If they're just looking for scaling, they don't have any trouble finding scaling. A little problem on focus sometimes.
So when you do like system loss analysis,
I'm sorry.
When you're looking at like the energy loss in the system, does it take into account the pumping losses from all that scale?
This is probably not pumped. Because say this water is supplied to the top drum, and in most, well, it depends. Some boilers are called forced circulation, mostly utility boilers. These industrial boilers, it's just water falls by natural circulation. Because also, if you've got water on one side of the tube and water and steam on the other side of the tube, this side is less dense because the steam bubbles take up a fair amount of volume. So you got more weight on this side than you got on this side, and it forces a natural circulation through the system. Now, but utilities do have these that have pumps on them. And yeah, I never thought about that. I would hope a utility would not let a boiler, look at this crap. That's awful. Yeah, they fired that guy. They should have fired that guy. If he's responsible for his water chemistry, and this is what's inside his boiler tubes. Yeah, I was hoping to get to the point where they pull the thing out. I'm not sure where it is. Well, anyway, I think I'll pull it out. Well, let's see. Look like he's pulling that. Let's see if this is it. Come on. Take up a long tube, isn't it? I'm about to get vertigo here. There we go. There. That's the boiler house. Yeah, you can't see much, but. That's just the casing, the shell of the boiler.
So for a water tube boiler in the combustion zone, do they build that much pressure in the combustion part of the boiler?
Say that again now. What?
For a water tube boiler, do they build up much pressure in the combustion zone of the boiler, like outside of the water tubes?
Okay. Well, no, there's not a lot of pressure. You know, I mean, they can be forced draft. It depends how many fans you got. If you've got like big utility boilers will have a forced draft fan blowing in and an induced draft fan sucking out. And so then the furnace will be what they call kind of balanced pressure. And the pressure is controlled by the capacity of this fan and this fan. If this fan blows more, that'll pressurize it. If this fan pulls more, it'll be negative pressure relative to the environment. But some boilers, smaller boilers, just have a forced draft fan, in which case that combustion zone will have positive pressure relative to the atmosphere. But I mean, it's not a tremendous pressure. You can still open a door. Now, if you open a door and the flames are in there and it's positive pressure, you better not stand too close because you may get a, you know, you may get a flame in your face. If it's balanced draft, it's probably, it may even be a little bit negative in pressure to protect people. So it's usually one of those two. All right, enough of that. Now I do have, we're not gonna, what I'm gonna do, I will forward you some emails. I have a YouTube video on water hammer, which is about 7 minutes. And it's pretty cool. It shows a guy rigs up an experiment that shows you, talks about water hammer and all that details. And I've got another one. I forget what the other one's on right now, but I'll send you all those two links. They're not real long, but they are very they're very interesting. Okay. So now having, come on. There you go. So now having seen that, look at this, potential energy loss resulting from scale deposits. And of course, we got different types of scale. It depends on the makeup of it. Normal scale, high iron, and iron plus silica. So a 64th of an inch. 64th of an inch is not a lot compared to what you just saw. Oh my gosh, there are places in there that scale's an 1/8 of an inch or more. An 1/8 of an inch, they don't even put it on the chart. So a 1/16 of an inch with normal scale, 3.9%, high iron scale, 6.2%. And the guy making this chart figured that nobody would ever run a boiler with a thicker scale than that. He didn't see Frito-Lay, did he? You know? So you can see that's the water side scale. Now think about this. What's going to happen to the wall temperature of the tube if I scale up on the water side? So out here I've got my combustion zone. Just pick a number, 3,000 degree gas. I've got the outside of the pipe. I've got the pipe wall. I've got the inside of the pipe. I've got the scale, and I've got the water. So if I scale up that boiler, what happens to the wall temperature? It goes way up, and you burn out tubes. That's another problem. Because see, it's the water that cools the boiler tubes. Now, boiler guys, they don't really care much about efficiency, but they care a lot about not melting their boiler. They care a whole lot about that. Because if you melt the boiler, you damage the tubes. Then you have to come down, you have to identify the tubes, you have to go in, you have to cut them out, and you have to repair them or replace them. So how can you damage a boiler tube? Well, the fireball is always 3,000 degrees. It's the water flow and the heat transfer to the water that protects the boiler tube. So when you go scaling up that boiler, you put this insulating blanket between the water and the wall, through the wall, and you got convection coefficient, and you got 3,000 degrees. That can't be good. It's not good, okay? So now, you can also do fireside fouling, which means you can soot up on the fire side. But what happens to the wall temperature of the tube if you foul up the outside of the tube? It goes down. So the boiler guy, the maintenance guy, he would much rather you soot it up than you scale it up, because at least you're not going to wreck the boiler tubes. I mean, he's going to have to go in at some point and clean the soot off, but that's a whole lot preferable to having to acid clean and potentially replace damaged tubes. So big difference between fireside fouling and waterside. Now, they both impede heat transfer, and they both will cause an elevated stack temperature, right? Because you burn the fuel, you let the heat loose in here, it's supposed to go into the boiler tubes and make steam, but it can't get in there because you either have fireside fouling, waterside fouling, or both, okay? So there you go. Fireside fouling is managed through soot blowing and periodic offline cleaning. You just have to clean that stuff off on the fire side. There you go, and you know exactly where those came from. I just cut and pasted once upon a time. It makes a pretty good slide though, I must say. Okay, flue gas temperature loss. Okay, here's one that you probably wouldn't figure out on your own. Often, an increase in flue gas exhaust temperature will accompany an increase in excess air supplied to the combustion zone. So think about it. You got a boiler operating, maybe it's operating at 50% load, whatever. Something happens and we increase the amount of combustion. Everything else stays the same, still 50% load, but the damper control on the fan goes wacky, and we're putting in more air than we should. Okay, so that will increase, typically will increase the flue gas exhaust temperature. And so here's what's going on. Heat transfer in the combustion zone is dominated by radiation. It's so hot. Remember, radiation is what? T high to the fourth minus, say, T tube to the fourth power relationship. And that 3,000 degree fireball temperature is so high that the T to the fourth, when you do that math and subtract, is such a big number that the radiant heat transfer is really large. So we say roughly 75%, you know, if you got a swaggy number, I mean, it depends, but the dominant mechanism for transferring heat inside that furnace area is radiation. So the flame zone temperature is an important factor. So then we say heat transfer is proportional to the fourth power difference between the flame temperature and the tube wall temperature. So a very small change in flame temperature will significantly reduce the heat transfer in the combustion zone. So if I put in this larger amount of air, I quench that flame temperature. I cool down the fireball a little bit, and that really knocks that T to the fourth temperature difference down. I transfer less heat by radiation. The convection can't make up for it, so that energy stays in the gases and goes up the stack. So you see an increase in flue gas temperature. More or less.
More or less, the boiler is running lean, kind of like an engine running lean.
Yes. Yeah, leaner than it should. Because lean Lean is relative to fuel, right? More air, less fuel.
Yes.
Yes, that's correct.
Run an engine lean, you
Yeah.
burn the spark plug instead of running it bridge, which you use fast.
Yeah, there you go.
So, okay, okay. Makes sense.
Okay, the most common factors influencing flue gas temperature, and this just summarizes what we've been through. So I'm not going to read back through those for you again. Okay, so the temperature loss management summary. So this is what we need to consider. Monitor and record flue gas temperature with respect to boiler load, ambient temperature, and flue gas oxygen content. Okay, so, well, we'll get into that. Compare flue gas temperature to previous similar operating conditions. But you got to get the parameters, the ambient temperature, the load, and the flue gas oxygen content to have been in a similar range to do a fair comparison. Maintain appropriate fireside cleaning, maintain appropriate water chemistry, and evaluate heat recovery component savings potential. And we will get into that. We'll use the measure tool to do that for us. Okay, combustion component. Okay, so stoichiometric combustion. Let's burn a little methane here. A little CH4, a couple of O2s. We're going to do it right. We get CO2 and 2 H2Os plus energy. Okay, that's doing it right. We don't have any of those COs over there. So in a perfect world, we would get perfect mixing. So every place you had a methane molecule, you would have an O2 or 2 O2 molecules right there, and they would just do that little combustion thing, and life would be perfect. Problem is, we just don't get perfect mixing in the real world, okay? But, so for stoichiometric combustion, theoretical error, because right, the amount of air that we provide for stoichiometric is called theoretical, and that's because we get perfect mixing. One molecule, just the right amount of oxygen, same thing here, all over the entire combustion zone. It's perfect. Actual combustion, not quite so nice, okay? So we still have our methane, we still have our 2 O2s, but we get some CO2 and we get some H2O. Now, what's this CO doing over here? That's not good. I don't want him. What? An H2? You mean some of my fuel didn't burn? What? A methane molecule? He couldn't find any oxygen. And then I got some spare oxygen that was over on the other side. It was too far away, and that H and that methane molecule just couldn't combust. So they're going up the stack hot. So unreacted methane. CO, you can burn CO. It's not a good fuel, but you can burn it. And hydrogen are fuels resulting from incomplete combustion. Okay, so that's not good. You can have safety, health, and efficiency issues. Safety, they can burn in the stack where you don't want them to burn. They're still fuels. You get the right mixture, you can have a fire in the stack. Health, you don't want to put that stuff out. People breathe it. And efficiency. So combustion management strives to eliminate unreacted fuel. And how do we do that? We start cramming more oxygen in. Because we know we're not going to get perfect mixing, so we got to have more oxygens floating around so that we can burn everything effective. Okay? Excess O2 provided to the combustion zone essentially eliminates unreacted fuel. So we're going to keep cramming in more and more oxygen until we burn all of the stuff appropriately. So all the carbon will burn to CO2, all the hydrogen will burn to water vapor, and we won't have anything else combustible left. So that's combustion. These combustion management principles in here are pretty simple in this course. Put in all the air you need until you burn all of the fuel. That's pretty simple. Okay. Combustion management principle number 2, but don't put in any more extra than you absolutely need. So be careful at how much you add. Okay. Because extra oxygen added to ensure a complete reaction of the fuel is heated by fuel from ambient temperature to the temperature of the exhaust gas, and then it goes up the stack. Well, where do we get the oxygen that we burn? Well, we can't afford bottled. You know, you could buy bottled oxygen and you would be much more efficient, but you can't afford it because it's free, right? It's in the air. So that's what we use. So in other words, to get 1 mole of oxygen, we have to bring in 4.76 moles of air. And 3.76 moles of them are basically nitrogen and trace gases. And you get some water vapor too, but that, you know, that's a separate accounting. We usually think about this as dry air coming in. So think about it. So in that equation, I need 2 O2s, so I've got 2 times 3.76, and that's called N2. In the utility industry, instead of just talking about nitrogen, they talk about atmospheric nitrogen. They talk about N2A. If you see N2A, that takes all of the dry gases except oxygen and just kind of lumps them together. You know, so it's not really just all nitrogen. There's a little bit of argon. There's a little bit of CO2. There's probably a trace of CO. I mean, whatever else is in there besides the water vapor is called atmospheric nitrogen. You'll see that term sometimes. I think I have it in these slides someplace. If you see N2A, it's atmospheric. And it has a slightly different molecular weight than straight nitrogen. Straight nitrogen is 28.1 something. And N2A is, I don't know, it's a 10th different because it's a weight average of all of the different gases that make it up, okay? But anyway, so we're bringing in all that nitrogen and gases cold and we're putting them up hot. Fact of life. Okay, so minimum oxygen evaluation. Minimum oxygen limits can be determined by measuring combustibles, okay? So what will happen, so the way we measure the excess O2 is we just put a probe in those flue gases and we pull a sample, and that sample will tell us what percent on a volume basis coming through there is oxygen. So, you know, if you were stoichiometric combustion, your perfect theoretical air, how much oxygen is left in the flue gas? None, because we burned it all up. That's what stoichiometric combustion is. But we can't do that. We have to put in some extra. So the amount that doesn't react in the combusting of the fuel is left in the flue gas, and we measure that with a combustion analyzer. And so it'll tell us. So you see flue gas oxygen percent down on the bottom. And then you see combustibles. Well, if I have too little excess, I'm not putting in enough, I guess I'm burning rich because I got more fuel than and I don't have enough air to burn it. And so my combustibles go through the roof. Look at the parts per million. At 1%, I'm about 60 parts per million. And if I start going down less air than that, it is just going almost asymptotic, going up like crazy. As I come down to 2%, I'm down to 20. Down to 3%, I'm down to someplace around 10. And then it pretty much levels off till I get to 7. Then when I go to 8, it's starting to come up again. And then I've got so much air blowing around in there, it's starting to be detrimental to being able to burn anything. Velocities are too high. It's just, there's not enough time at temperature. I start to not be able to burn it because I have so much air. So someplace in there is kind of a sweet spot where I want to operate. Okay, so here's another example, fuel rich, air rich. And you see, so notice we've got, on this one, we got the red graph, which now they've added CO and combustibles. So, I mean, what's happening is as we cut air back enough, then we don't even have enough oxygen around some of the carbon molecules to burn them to CO2. They start burning to CO, which is not good, okay? And then as I put in more and more and more, the CO and combustibles go down, but NOx goes up, efficiency goes down because I'm just blowing so much air through there. And so you see the efficiency is peaking someplace, it depends on the system, 2, 3, 4, 5%, okay? And so I still have a little bit of CO, I could have less CO, but then I have to put in more and more air, and I've got more and more nitrogen going through the system, and I start carrying away more and more heat. So I don't want to go further that way. I can't go less than the ideal, because then I start gaining in CO and combustibles. So there's kind of a sweet spot in there, someplace probably between 2 and 5%, depending on the system. Okay. Babcock and Wilcox a long time ago, for proper combustion, three factors dominate the combustion process. They call these the 3 T's of combustion. And you got to get these right to have good combustion. You got to have time, temperature, and turbulence. Time at temperature for the combustion, for the oxidation reaction to complete. It takes time. It's not instantaneous. Reaction temperature, you got to be above that combustion threshold. So you've got to have that fuel and oxygen together for enough time at enough temperature, and then for it to oxidize. And then we have to have good mixing. We have to have turbulence to keep all of that stuff mixed up so that I have oxygens in close proximity to fuel molecules so that they can oxidize. So a deficiency in any one of those factors will cause your combustion to be a deficiency, or your combustion will suffer. So time, temperature, turbulence, 3 T's of combustion. Okay, I'll tell you what, let's just stop right there. We've pounded it pretty good today. So look at that homework assignment. We've got enough now that I can go through. Until we got through some of this, you needed this background before I could even read it to you, and it would be meaningful for you. So we'll go over that next time and keep pounding through the boiler slides. Now, as far as testing is concerned, at the end of the steam section, you have a big test. At the end of the pumping section, you'll have a big test. At the end of the compressed air section, it's the end of the course, and that's on the final exam. So we're still 2 to 3 weeks away, but if I'm not careful, I spend all my time in steam, and I don't have any time left for anything else. And so I'm trying my best to get through steam so I can balance the course out. So we're gonna keep pushing pretty hard to get through the steam slides. Okay, y'all have a great rest of the day, and I'll get this posted and see you on Thursday.